All right, we're going to talk about two different equations here and how they can be related or how they can be visualized as graphs on the Cartesian plane, right? I have both of these equations depend on x and y. So I've got two variables there. So I can visualize the relationship between x and y that satisfy these relationships with a two-dimensional system. So the Cartesian plane does exactly that. Let's start with number one. Okay, so we're going to graph this. Let's first open up an xy plane. So the y-axis will be the vertical, the x-axis will be the horizontal. We'll make that way positives. We'll make up positives, which means this is negatives, and these are negatives. Right, that origin right there happens at 0, 0. All right, now we can tell from that first equation that this is a circle with x-coordinate, or the x-coordinate of the center is 0, and the y-coordinate is equal to positive 3. So 1, 2, 3. That's the center of my circle, and my radius is equal to the square root of 4, which is 2. So 1, 2, 1, 2. So we get something that looks like that. Remember, the center of the circle is not on the equation. That does not satisfy. One, two, three. There's the center. Okay, so all of these points on that circle satisfy that equation. Right, for instance, let's pick a point. What would this point be? If I fixed the y-coordinate as 3, then the radius is 2, so it has to be 2, 3. Let's make sure that 2, 3 is indeed on that circle. Right. Let me rescale these a little bit. That's the x-coordinate 2. Right, if my x-coordinate is 2, and my y-coordinate is equal to 3, and this is what I get. I get 4 plus 0 squared is equal to 4. Right, 4 is equal to 4. So the point 2, 3 does satisfy that equation. It is on the perimeter of that circle. Now, this gives me a graph of a map, not a function. Right, because the function is a map that sends x values or inputs to only one output. But look at this input of 1. When x is equal to 1, it intersects my function here, and it intersects there. In fact, let's go ahead and figure out what those 2 points are. When my x value is 1, what am I going to get for a y value? So this is 1 squared is 1. I subtract 1 from both sides. I find y minus 3 squared is equal to 3. I take the square root, and I add 3. Oops, forgot to do a plus or minus. So that point right there is the point, my x value is 1, and my y value is 3 minus the square root of 3. That point right there, my x value is 1, and my y value is 3 plus the square root of 3. Right, so this is not a function because I'm trying to send 1 to both 3 minus the square root of 3 and 3 plus the square root of 3. It is a map, not a function, right? It does not pass that vertical line test. But I can make it a function if I restrict myself to the positive y values. In fact, let's try to write this equation as y is equal to a function of x. So if I rearrange this and solve for y minus 3 squared is equal to 4 minus x squared. I take the square root, y minus 3 is equal to plus or minus 4 minus x squared. And this is the reason why I wouldn't be able to write it as a function as it stands, right? I pick up this plus or minus. So I get 2 different y values for a single x value. So let's just choose the positives. So y is equal to, if I add the 3 to the other side, 3 plus the square root of 4 minus x squared. Now that I've made that choice, this equation right here, in fact, let's underline this in blue. Now y is a function of x. And in fact, it is the upper half of this circle. Right now, if I evaluate this function at x is equal to 1, I'm only going to get one y value, not two different y values. So in fact, let's evaluate this function at 1. F at 1 is 3 plus square root 4 minus 1 squared. That's 3 plus, what's that going to be? Square root 3. Exactly what that point was, right? We omitted that point because we didn't take the negative y values. We said that we're only going to take the positives. Or rather, we chose that positive sign right there. Okay, so let's get rid of everything and let's just write the function. So I'm able to write the top half of that circle as a function of x. This is the function where y is equal to 3 plus square root 4 minus x squared. Okay, let's get everything off the page. And let's talk about properties of this function. So first, let's think about the domain, right? Every function has a domain and a range. So what kind of x values does this function accept? Well, seemingly, it exists over these x values. All the x values from -2 to 2. And let's show ourselves that. If y as a function of x is equal to 3 plus square root 4 minus x squared, when I think about what could go wrong with this equation, I need what's inside the square root to be positive. I need 4 minus x squared to be greater than or equal to 0 in order for this function to give me a real number, right? Because I can't take square roots of negative numbers. So whatever 4 minus x squared is, I need it to be positive. And now I can rearrange this and solve for x. So minus x squared is greater than or equal to -4. I multiply both sides by -1. X squared is less than or equal to 4, right? Remember to flip that sign. Now, if x squared is less than or equal to 4, that means x has to be trapped in between -2 and 2, right? Because if I look at -3, that squared gives me a 9, and that's not less than or equal to 4. If I look at +3, then that gives me a 9, which is not less than or equal to 4, right? But if x is smaller in size than -2, or sorry, if x is smaller than 2 in absolute value, then this function will make sense. In fact, this tells us the domain is all x values between -2 and 2, inclusive, right? If you plug in -2 or 2, then you get a 0. Okay, let's think about the range. So let's label this. This was us working on the domain. And if we work on the range, this is, I'll switch to blue. What kind of y values does this function give me? Well, it seemingly gives me anything. So I can get a 3, right? The y value of 3 actually gets hit twice. It gets hit over here at -2, and it gets over here at +2. In fact, if you went back up to this equation and plugged in -2 and +2, you'll get a 3 as a y value. And the highest y value that I get, well, the center of my circle is at 3 and my radius is 2, so the highest y value should be a 5. That's going to be, well, from the picture, it looks like it happens when the x value is 0, right? It's on my y-axis. So let's evaluate this function f at 0. What do we get? 3 plus square root 4 minus 0 squared gives me 3 plus square root 4, gives me 3 plus 2, and that does indeed give me that 5. right? But that's the highest that my y value can be. So that's my range, all values between and including 3 and 5. All right, oops, did not want to do that. All right, there's our function. Let's think about the symmetry of this function. So notice for positive x values, the negative of that x value gets mapped to the same point, right? It's symmetric over the y-axis. So this is an even function because f at x returns the same thing as f at minus x, right? You get the same y value for these two opposite x values. So it's an even function because we're symmetric over the y-axis. Let's talk about increasing or decreasing. All right. Where is this function increasing? Where is it decreasing? So as I move forward in my x direction, where's my function going up? It's going up here, right? This is the section where it's increasing. So I'm increasing on which part of my domain? From -2 up to 0. I have my maximum at 0, and then I start to decrease. Right, from 0 to 2, I'm decreasing. All right, and we've already mentioned it. We have a maximum at 0. So let's talk about extrema. So do we have local maximums? So go back up to our picture here. We can see that the point 0.05 is a local maximum. That point right there is bigger than everything else around it. So we have a local maximum at 0. The value of the maximum is 5, right? That was what the function gave me at 0. All right, and where do we have local minimums? So I've got a local minimum here because that point is smaller than everything else around it, and here because that point is smaller than all of the other function values around it. So we have local minimums at -2, 3, and at 2, 3. All right, and both of these are going to be global. So this is also a global max because not only is it bigger than everything else around it, it is the biggest point. There's no x value that gets mapped to a point bigger than 5. Both of these are global minimums, which I guess if you define global minimum as it has to be unique, then you could say that the global minimum does not exist here because it can't exist at -2 and at +2. But at -2 and at +2, your function returns the smallest y value that it can, which is 3. All right, let's switch gears and talk about the second function. The second function is already written y as a function of x. Y as a function of x is x cubed minus 3x. All right, now if I want to graph this, let's pull out an x and write this as x squared minus 3. So one of my zeros comes from x being 0. Right, if I evaluate this function at 0, I get a 0 for my y value. And then I'm going to get 2 more zeros here. We can complete the square or we can factor that. Either way, you're going to find that your two zeros here come from plus or minus square root 3, right? If you set that term equal to 0 and solve that. So the graph of our function, there's positive, not negative. That's positive square root 3. This is minus square root 3. The function looks something like this. In fact, if we were to plot a few points, let's look at -3, -2, -1, 0, 1, 2, and 3. So if I evaluate this function at -3, I plug -3 in for these x values, then what is that going to give me? And you can use either form, that form or this form. Let's use this form here. So -3 cubed gives me a -27, and then minus another 9, that gives me a -26. All right. At -2 cubed is -8. Oh, I made a mistake. Let's go back up to that -3. -3 cubed is -27, but then minus a 3 times a -3 is actually a +9. So what do I get there? -27 plus 9 is 16. No, 18. -18. If I look at -2 cubed is -8 plus a 6. That gives me a -2. If I look at -1, I get -1 plus a 3. That gives me a 2. If I look at 0, that's 0 minus 0. Oh yeah, we already knew that was going to be 0. Right, because we had that point right there. And if I look at +1, I get 1 minus a 3 gives me a -2. If I look at +2, that gives me an 8 minus a 6, which gives me a, oh, wait a minute. That give me a -2? No, +2. And if I look at 3, I get 27 minus a 9. That gives me a 16. No, 18. Can't do math. All right. So -3 over here gets mapped down to -18. -2 gets mapped down to -2. -1 gets mapped up to +2. 0 gets mapped to 0. 1 gets mapped down to -2. So in fact, let me amend my graph here. This is going to dip down a little bit further. At -1, we get a -2. And then at 2, we get a 2. So over here at 2 gives me a 2. And over here at 3 gives me a 18. So notice that -3 gave you a -18, and 3 gave you a +18. -2 gave you a -2, 2 gave you a +2. So this is an odd function, or so it seems. And in fact, from the graph of the equation, you can tell that that's an odd function. This part of the graph is reflected over the origin. Right? This graph right there is symmetric over the origin. It's an odd function. So in fact, that's our symmetry type. It's odd. And notice that in the equation, all the terms here are odd, right? X cubed and x to the 1. Okay, so we've talked about plotting points on the graph. We haven't talked about the domain yet. All right, the domain, what kind of x values can you feed this function f? Well, I can plug any number that I want into those x's, and it's going to give me a real number out. So the domain is going to be all real numbers. Right? The domain, this function is going to exist over my entire real number line. Let's try to clean up the graph a little bit. Okay. What about the range? Well, the range is going to be all real numbers as well. Minus infinity up to positive infinity. Right? If I can have as large of an x value as I want, this function is going to increase without bound. It's going to go as high as we want it to. And if I can have as large of an x value as I want in the negative direction, this function is going to decrease without bound. There's going to be no stopping it. So there is no minimum. In fact, let's talk about maximums and minimums. Where are my local maximums? So it seems like I have a local maximum right here, right? At that point, it's taller than everything else around it. So I've got a local maximum from the graph, it looks like, at the point -1. And I can figure out that local maximum by evaluating the function at -1. What do I get? Oh, in fact, we've already done that. Gives me a 2. That point right there is a local maximum of 2. And that's the only local maximum that I see. Let's do local minimums. So from the picture of the graph, it looks like this point right here at 1 is my local minimum. It is smaller than all of the other function values around me. So I've got a minimum at x is equal to +1. And what is the minimum value? It's the function value at +1, which from our table is -2. All right. What about global extrema? Let's think about, does there exist a point on the graph of the function that's taller than every other point? Not just the ones around it, but every other point. So here we see that none exist, right? This function increases without bound. We've already talked about that. So there is no maximum. It goes as high as we want it to. And for the exact same reason, there's no global minimum either. This function is going to drop down as far as we want it to, right? The further we go in that direction, the more this function drops down. So there is no minimum value everywhere, but we do have some local extrema.